All right, so I've just got a little demonstration here where I'm going to use a small circuit just to show resistance in series versus resistance in parallel. So what I'm about to show is based on these two circuits. On the left side, or here, I have one circuit with a 0.75 watt light bulb. Okay? And in that circuit, there's a 100 ohm resistor, and they're wired in, as we can see, in series. So the resistances will add. So if I take the total resistance of the system, here I have a 75 watt light bulb. I need to do a power inversion for 2.4 volts, which is my EMF of the system. All right, so I use P equals IV, and I'm able to calculate in using R over VI. I'm able to calculate a resistance of 8 ohms of the light bulb, added to the 8 ohms of the resistor in series, and there's a total resistance of 108 ohms in the system. All right, and I'm going to assume that the internal resistance of this battery is negligible. And then on the right in this circuit here, what I'm going to do is I'm going to take the same 75 watt light bulb and this 100 ohm resistor, and I'm going to wire them in parallel across the same EMF, which is 2.4 volts. And again, we're going to assume that internal resistance is 0. So the total resistance of this circuit is 0.135. Okay? And so that tells me over here, if I try to calculate the currents that are going through, if I do the calculation here, I can see that my V over resistance, my current is 0.02 amps rolling through. And the bulb itself needs 0.3 amps to illuminate. So that's going to tell me that if I set up this system, the bulb is not necessarily going to light because it needs at least 0.3 amps to illuminate. Okay. On the right side here, if I do the same calculation, I over the resistance, I get a current of 17 amps. And 17 amps, it's going to be split. If we look at Kirchhoff's first rule, it's going to split across this junction. We're only 0.3 amps that we talked about here are going to run through the light bulb, and the rest is going to run through that 100 ohm resistor and to maintain my voltage drop on the other side. All right, so that's what I just want to show this, that it's real and it's not something that we just make up, and that the equations do actually end up showing that. All right, so I've got this little miniature at-home circuit set, okay? And what I want to show is that we have a battery. Here's the 2.4 volts of our battery, okay? Those are wired in series through here. They're going to go through a switch, and I just have the switch so that the light only turns on when I want it to, but it has no resistance and provides no power changes to voltage, okay? And I've got these black and this red wire that are going to connect the switch in the battery to the circuit, okay? And so if I look at the circuit as I have it drawn here, just the light, with just the light, it'll turn on. Okay, so you can see the flash. The power is coming through the batteries. There's a voltage drop across this resistor, and it goes back. Okay, but if I do what if I now take this guy here, okay, and he is a 100 ohm resistor, okay, and I put him, and now I'm going to wire him so that he is in series with my light bulb, so his resistance is going to compound, just like we showed previously. Okay, so I've got to use just another wire here to connect it. I'm going to connect it in series, and when I turn on the press switch, see, my light does not turn on. Okay, and so that's what we expected, that the 0.3 amps of the current that's going through would not light the light bulb. If I had an ammeter, if I had an ammeter, I'd be able to measure that. In fact, there was voltage going through or amperage going through the system, just not nearly enough voltage to actually make that light turn on. And this is irregardless of where I put the resistor. I just want to show that even if the resistor is coming after the light bulb, I end up with the same result. So if I put the resistor down here, so essentially the current goes through the light bulb first and then through the resistor. It's the same idea. So it's not as though the resistor is sucking up the energy or sucking up the current beforehand. They do work as a whole system, and they're only that current is the current for everything in the system. Okay. So now I ask, okay, let's go back and let's wire this. Again, this resistor, let's put it in parallel. All right. So I'm going to connect it in parallel. So now we can see my feed comes into the circuit. The current goes through a junction point, goes through the light, goes through my own resistor, comes back and flows through. And we estimated that there'd be 17 amps of current going through. And if I push the light comes on, and it comes on just as bright. It's not dimmed or anything like that. So we can see that the resistance does make a huge difference whether it's put in parallel or in series, and that our equations that are worked out are real things that we can verify experimentally. Okay, and so you can think about this as like water through a hose, where you've got water coming into a system and it splits evenly over the two pipes and comes down, versus having to go through a large resistance and you lose your flow under the same pressure. Okay, so if you think about that in the terms of them being in series, you have a certain amount of pressure moving the water, and you can think about the ohms as the size of that pipe, and as the size of the pipe grows and the pressure you're putting on the system grows, what's going to come out the other side is going to drop because you're going to have less pressure coming out, and that's essentially what how you can think about your current. You can think about the current of water and the current of electricity sort of conceptually the same. So I just wanted to show that, and I hope that sort of is a good demo for you to visually see that resistance in parallel and resistance in series are distinctly different.